How's it going, everyone? Welcome to my very first try at Edpuzzle. If you're unable to get into Edpuzzle, this is going to be uploaded as a separate video on YouTube that you can watch and just answer the questions on your own in the time where they would normally be paused by the Edpuzzle. I'll have instructions on how to do that in your teams. So we're going to carry on our understanding of forces that happen inside and between molecules, intermolecular forces. This lesson is loosely based on Apex 3.2.3, intermolecular forces. So if you're interested in further reading, then you can go ahead and check that out. But this is meant to be kind of a replacement of that. So the things that we're going to do is we're going to answer 3 guiding questions. What are intermolecular forces? How can we tell if a molecule is polar? And then in a separate video, we're going to talk about what kinds of intermolecular forces exist and how can we tell what's present in a substance. So that's going to be a separate video. So we're going to answer 1 and 2 today. What are intermolecular forces and how can we tell if a molecule is polar? One of the things you might have heard me talk about is that the difference between intra and inter is that the prefix of the word means something different. So intramolecular forces were what we were looking at in the week before we went to fall break. Intramolecular forces are the forces inside molecules. You might have heard the prefix intra when you hear someone talk about intrapersonal knowledge. That's how you deal with yourself. So, how I deal with the knowledge inside myself. So, intramolecular forces follow that same rule. The prefix intra means inside. Then, on the other hand, we have intermolecular forces, and that is between molecules. The prefix inter means between. So while intramolecular forces are kind of what we were talking about with electronegativity, intermolecular forces takes what we've learned about how molecules may or may not have differences in electronegativity or bonding, and then use that to think about how molecules are going to interact with each other when they're all the same substance. So that answers our question number 1, what are intermolecular forces? Question number 2, we're going to move on to that at this point. And to do that, I want to take a quick review of intramolecular forces. So we're going to do that right now. Okay, so let's start with a molecule that we're all pretty familiar with, and that is water, which is H2O. And this is what water looks like. You might see water looking like a molecule, something like this, but I'm going to take a second and I'm just going to do a slightly different drawing of it that you'll see right here. And that drawing emphasizes bonds here and here. And what I would like you to do at this point right now is pause the video and answer the question, is this a covalently bonded or ionically bonded molecule? So here's a copy of the question I just asked, and this will correspond to either the Edpuzzle or a form that I'll create and upload for you. Is water, H2O, a covalently bonded or ionically bonded molecule? Go ahead and pause and answer this now. Then the next thing I want to answer or have you answer is, how do you know if it's a covalently or ionically bonded molecule? This is review from lesson 3.2.1. So if you are struggling with how to find the answer, go ahead and review a couple of the screens from that Apex lesson to get yourself the answer you need. Okay, so this is the time where you'll check your answer that you provided. The answer to question number 1 is that water, H2O, is a covalently bonded molecule. I know that it's covalently bonded because I look at the electronegativity difference in these two OH bonds, and I find that the electronegativity difference is 1.24. I checked both of the electronegativities of each element in this bond on my periodic table, and I found the difference between the two was 1.24. And then the last thing that I know is that my value of the difference is under 1.7, so I know it is a covalently bonded molecule using my 1.7 rule. If you didn't get this one right, what I would do is I would just go back to my Apex lesson 3.2.1 and check out the sections where we talk about the difference between covalent and ionic bonding. For this next section of the video, I'm going to go back to this drawing of the H2O molecule that is like a bubble model, and we're going to use this to talk about what electron sharing looks like, because that is what a covalent bond does. Covalent bonds are where electrons are shared, not given up or stolen. Here's what a model of the electron sharing looks like, and I have two different bonds that I'm going to show you really quick. The first one is electron sharing between two molecules or two atoms of chlorine, and you can see that they create full octets for each other by sharing one electron each. And because they have the same electronegativity, they share their electrons evenly. So there's this like bubble that's drawn around the electrons, and that's just kind of representing what that like electron cloud between the two elements in this bond would look like. They share very evenly with each other because they have the same electronegativity, and one atom isn't pulling harder than the other atom. Here's a different example of what happens when we have uneven sharing. So when we have uneven sharing, or we have a difference of electronegativity that's greater than 0 and less than 1.7, we have what is called uneven sharing. Because chlorine has a higher electronegativity, you can go and look it up, you'll see that it pulls harder on the electrons that are in the bond between hydrogen H and Cl chlorine. And this is an uneven sharing. So it turns out that we have names for what happens when we have even or uneven sharing. They're both still covalent bonds, but one of them, this one where there's uneven sharing, is what's called polar covalent. So we have uneven sharing creates what is called a polar covalent bond, and even sharing results in what's called a nonpolar covalent bond. So the follow-up question is how do we know if something's polar or nonpolar? If the difference is anything other than 0 between the electronegativities, then we know that we have a polar covalent bond. So if the electronegativity difference is anything but 0, the bond is polar covalent. Let's look at what that means in terms of chlorine. I went ahead and I looked it up for you and found out that chlorine has an electronegativity of 3.16. So because I have two molecules or two atoms of chlorine in this molecule, then I'm just going to label them. All right, I have chlorine and chlorine. 3.16 minus 3.16 is going to be equal to 0. So I can safely assign this as nonpolar covalent. Now let's go ahead and go look over at that HCl bond that I was just talking about. Okay, we know that we have uneven sharing of electrons in the HCl bond, and I look at hydrogen, and hydrogen has an electronegativity of 2.20. Chlorine still has 3.16. So I do 2.20 minus 3.16, and remember I'm always only looking at the absolute value because this difference in electronegativity isn't really negative or positive, it's just a number in a direction, and the direction is in chlorine because it's the more electronegative of the two atoms in this bond. So because I have anything other than 0, this is going to be a polar covalent bond. All right, so that's the example. The next thing that I want you to do is we're going to do one of the pause and answer type questions. I'm going to have you classify which of the given bonds are polar. These will be in the form for you too, but what I want to know is which of these bonds are polar. I have fluorine-fluorine bond, a carbon-nitrogen bond, a hydrogen-fluorine bond, a nitrogen-nitrogen bond, a chlorine-chlorine bond, and a hydrogen-nitrogen bond. So you'll just go ahead and check off the check boxes for the appropriate ones. Go ahead and pause and take care of that now. All right, let's review our answer. Remember that an electronegativity difference of anything other than 0 is going to be a polar covalent bond. So really the only time I'm going to see an electronegativity of difference of 0 is when I have two of the same atom in a bond. So my fluorine-fluorine, chlorine-chlorine, and nitrogen-nitrogen are all nonpolar, which means that my carbon-nitrogen, hydrogen-fluorine, and hydrogen-nitrogen bonds are all polar covalent in nature. If you didn't get this right, that's okay. We'll have some more time to practice. All right, let's go back to the water example. The first question that I'm going to ask you is, are the oxygen-hydrogen bonds polar or nonpolar in nature? So the first question that I would like you to answer, so this is pause and answer question number 4, is the OH bond polar or nonpolar? And then of course you know that I'm going to ask you the follow-up, how do you know? How do you know? Let's check our answers. We know that the bond between oxygen and hydrogen is polar covalent, so it is a polar bond. And we know because the difference in electronegativity between oxygen and hydrogen is greater than 0. The electronegativity difference is greater than 0. In fact, it's 1.24. Next question. Okay, pause and answer number 6. What element in the OH bond pulls harder on the electrons in that bond? Take a second to answer this and we'll check our answer. Oxygen has a higher electronegativity. So because it has a higher electronegativity, it's going to be the one that pulls harder on the electrons in that bond. Awesome. Let's talk about the next thing on our list. We determined that in water, the oxygen in the bond pulls harder than the hydrogen in the bond. So then what happens is in that bond, we get an area where there's a tiny positive charge and a tiny negative charge because electrons are negatively charged. So I want you to pause and answer, which part has the more negative charge and which part has the more positive charge? Okay, so pause and answer this question. Which part of the OH bond has the tiny negative charge? Is it oxygen or hydrogen? If you answered oxygen, you're correct. Because oxygen has the higher electronegativity, it's going to pull harder on those electrons. And what happens is that a tiny negative charge is created because electrons are negatively charged and more of them happen to be in the same place. So if you answered oxygen, you're right. Well, most things in science have to have names, just because it's easier to talk about them by their specific names than anything else. So when we assign a label to talk about that tiny negative charge, we use a symbol, a Greek symbol, the small letter delta, and it looks a little bit like that. Delta just means partial. So we have a negative charge, partial negative charge, and then we have a partial positive charge by the hydrogen. And I'm never going to ding you because your deltas look weird, because I mean, really, look at these deltas. So because the oxygen has this tiny negative charge, or the delta negative, and we have hydrogens with a tiny positive charge that's represented by delta positive, what happens is we have an overall trend in a tiny positive and a tiny negative, because those the differences are kind of both in the same direction. So if we were to put one big arrow where the head of the arrow was pointing toward the negative charge, and the positive part of the arrow, it looks like a little positive right here, it would be pointing in one direction. And we can do that sometimes depending on the molecule. We call this a dipole moment. And all that the dipole moment means is that because of the difference in electronegativity between oxygen and hydrogen, and because that H2O has kind of a bent shape and both of the negative areas are kind of in the same place, we have this overall charge. So we use the arrow with the little plus on the end to represent what's called the dipole moment. Okay, so that brings us to the answer for that second guiding question that we talked about at the very beginning. How do we know if a molecule is polar? We can answer that question by saying that if a molecule is polar, it has a dipole moment. Let's go ahead and take this concept and apply it to a molecule that doesn't have a dipole moment and talk about why. For this example, we're going to look at a molecule called boron hydride, which has the chemical formula BH3. So it has one boron and 3 hydrogens. Remember that I don't expect you to draw a molecule from just knowing the chemical formula. So I've gone ahead and I've drawn this out for you. Boron with 3 hydrogens, or BH3, has them kind of in a triangular arrangement. And we're going to talk about molecular shape way more in our next lesson. But go ahead and take a second and find the electronegativities of boron and hydrogen and figure out who's more electronegative. All right, so I went ahead and looked it up, and boron has an electronegativity of 2.04. while hydrogen has electronegativity of 2.20. So I can still assign those little partial charges. All my hydrogens have a partial negative charge because the electrons get pulled towards the hydrogens, because as you can see, 2.20 is greater than 2.04, which means that my hydrogens are actually pulling harder on the electrons than boron is. So I have a partial negative charge on my hydrogens and a partial positive charge on the boron. And you can see that it kind of pulls in 3 different directions. So there's no unified direction. So pause and answer. Does this molecule have a dipole moment? Does BH3 have a dipole moment? If you're looking for a hint, consider that the positive and negative partial charges all go in opposite directions. The answer here is no. Because these positive and negative charges are all pulling away from each other, it's like having a three-way tug of war where all of the people on the ends are stronger than the person in the middle. The ropes don't move, and because the ropes don't move, there's not overall movement in any one direction. So because there's no movement in any one direction, we know that there's no dipole moment and this molecule is nonpolar. So to sum things up, to answer the question of how do we know if a molecule is polar, we know a molecule is polar when it has a dipole moment. We know it has a dipole moment when the bonds are polar, the individual bonds in that molecule, and they're all pulling in a unified direction. So we know a molecule has a dipole moment if the individual bonds are polar and if they're all pulling in kind of the same direction. That's going to be it for today. We're going to practice this a lot more the next time we meet. Have a great afternoon, everyone, and I will see you in the next one.